Like many other concepts in algorithms, the concept of aggregate analysis within the topic of amortized analysis can be better understood with the help of an example. As an example, we would like to use the case of the stack data structure. Say, for example, we have a stack, and what we would like to do is perform n number of push and pop operations. So we have one push operation and then another pop, maybe a few push operations and then a few pop operations. So overall, we have n number of push and pop operations. So clearly, for n operations, the time needed is big O of n, or even big theta of n, because every push and pop operation takes big O of one time, a constant time. That's because for either push or pop, all that we have to do in the stack is increase the pointer by one state or decrease the pointer by one state. Now visually, say we start with an empty stack that looks like this, and then we perform a series of push and pop statements. First push statement, second push statement, a pop statement, and so on. So if we represent the push statement using the sign push sx and the pop operation as pop s, then both of these operations take big O of one time. That is a constant time. So a sequence of these operations, a sequence of n push and pop operations take big O of n time. In fact, this is actually big theta of n time. Now we would like to add a small twist to this data structure. We now add a new kind of operation that's possible on this stack data structure. And this new feature of this data structure is multi-pop. In other words, at a given time, if we want to pop out k number of items at once, then we can use this multi-pop method to pop k number of elements from the stack. So what we do is introduce a new method, multi-pop, that takes stack s as input and number of elements k as input. And while the stack is not empty, this keeps popping items from the stack. While stack not empty and k is more than 0, keep popping items from the stack and decrease k. So this is our multi-pop operation that simply keeps popping items k number of times. So the question that we would like to ask is, if we start from an empty stack and we perform n number of operations, either push, pop, or multi-pop, if we perform n number of them, what will be the cost of these n operations? Will it still be big O of n or big theta of n, or more than that? That's the question that we are looking for an answer. Now let's see how much time the multi-pop operation can take at max. So if we have total n number of operations, and let's say in one operation at max we can pull out all the n number of elements, right? So that means the worst case running time of a multi-pop operation is big O of n. Now, since there are total n operations and each of them could be a multi-pop operation, that means we have total n operations maximum. Each of them could take big O of n time. So this means that the maximum number of operations that could be happening can be expressed as big O of n squared. So this is the worst case cost. So worst case cost of our n number of operations of sequence of push, pop, and multi-pop. But this is not tight. This is not tight calculation. Obviously, this is big O, so this is the maximum or worst case possible. Now, this analysis definitely is correct. So this is a correct analysis, and such an analysis is known as average case analysis. Now, if we observe carefully, although a single multi-pop, one multi-pop operation can take a maximum of n time, a sequence of n push, pop, and multi-pop operation can take at most big O of n time. Here's why. Say we have an empty stack like this, and then we push, let's say, 2 or 3 items. Then if we multi-pop all 3 items, then we are done with all the items in the stack. In other words, we can multi-pop k number of items from a stack only if they are in the stack. If these k number of items are not in the stack, then we cannot pop them. So say, for example, I keep inserting items, 1, 2, 3, 4, 5. I cannot multi-pop 5 items at the beginning. I cannot multi-pop 5 items after the second insertion. I can only multi-pop 5 items at the end of the insertion of the 5 items. So these push operations will take me 4 time, and then the last one, multi-pop, might take 5 cost, but then still I couldn't do 5 possible multi-pops when I'm actually dealing with total 5 elements in the stack. Also, we have to keep in mind that multi-pop eventually actually does pop. So no matter how many times we call multi-pop during this process, the total number of times pop can be called is maximum n. So with this rationale as well, we can clearly see that the total cost of any sequence of n push, pop, and multi-pop operations is just big O of n. Now, such an analysis is called the aggregate analysis. So the goal in aggregate analysis is exactly to show this. That is, a sequence of n operations takes worst case Tn time. Now this cost, if we calculate in terms of per operation, so then the amortized cost or the cost per operation is Tn by n. This is the cost per operation on average, or amortized cost. So once again, if we have a sequence of n push, pop, and multi-pop operations, then at most the maximum number of elements that we can put into the stack is n, because in the worst case scenario, it all may be push operations inserting one element each time. The maximum number of elements that we may have in the stack is n elements. So even if we run multi-pop many times, the worst case scenario of multi-pop, that is popping n elements out, cannot happen all the time. That's because if I have maximum n elements in the entire duration, then there's no way the worst case of multi-pop can happen each time, that is during each operation. So for this reason, the maximum cost of a sequence of these operations is only big O of n or big theta of n. So the purpose of amortized analysis, as we saw with the case of aggregate analysis, is to show that even a single operation, even though a single operation may appear to take a lot of time, if we take into consideration the sequence of operations that we perform, on average, one operation may not take as much time. Now, remember, amortized analysis does not happen in code. That is, we do our own analysis to perform amortized analysis. And many times, performing an amortized analysis enables us to understand how a particular data structure that's implemented in the algorithm is working, and then eventually come up with a slightly more efficient or optimized design of the overall algorithm.